Speeding at sea, it's me, Z. Today is the third video of my special relativity series on the mind-bending world of black holes and Penrose diagrams. Whether you're a student, enthusiast, or just curious, buckle up, because we're about to journey to the edge of space-time itself. If you haven't already, I highly recommend that you watch the two videos prior to this one, since it'll give important context. We have so many epic things to talk about, so let's just jump straight into it. In my previous videos, I showed you space-time diagrams that had x, position, on the horizontal axis, and t, time, on the vertical axis. We played around with many useful examples like time dilation or causality at relativistic speeds. Now, the one thing in common with all of these examples was that they were all one-dimensional. We only did the position along one direction. And these space-time diagrams were called Minkowski space-time diagrams. Now, what if we wanted to describe events in truly four-dimensional space, x, y, z, and time? Or potentially infinite distances, such as the entire universe. In this case, we'll need a new kind of map, a Penrose diagram. This is how we can represent space-time by compressing infinite distances and times into a finite visualizable space. So let's start with our original space-time coordinates and transform our coordinates with the inverse tangent functions. Now, inverse tangent is unique because it allows us to take on infinite values of distance and time within the finite values of negative pi over 2 to pi over 2. The function looks a bit like this. In our case, we can visualize infinite time and space on a finite plot using the transformations of inverse tangent. Now we have at every x and y intercept representing infinite distance or infinite time. Now, similar to before, this I plus that I've just labeled here on the y-axis is positive time, but it now represents our infinite future. The I minus here is negative time, but now represents our infinite past. I is not a specific point, but an idealized point at the universe's infinity. On the position axis, we now have plotted distance space to the left and the right. You may notice that our distance scales are now becoming highly distorted, becoming more so as we go from the center to the edges of the diagram. The path of light rays are always represented by 45-degree angles. For example, in my previous videos, we said that for every light nanosecond in time, we would travel 1 light nanosecond in distance at the speed of light. This is the same idea that we can translate from our Minkowski spacetime diagrams to our Penrose diagram here. Similarly, we can define causality and event separation in the same way as we did before. In the second video, I mentioned that events are separated in 3 ways: time-like, space-like, and light-like. We discussed that only light-like and time-like events can be causally connected due to the speed limit of light. We can now visualize these conclusions on the Penrose diagram by drawing light cones relative to this event A, representing A's future and past. These 45-degree lines represent how light travels from A. Now, these 4 different regions correspond with the different event separations that we talked about. For example, these are the events here that are reachable within the speed of light, whereas these are the space-like events outside of the light cone, where it is not possible to visit any event in this region to location A because they cannot be causally connected. Again, this is because of the speed limit of light. Let's start with a simple, non-rotating, uncharged black hole, or a Schwarzschild black hole. This black hole has 2 key features: the event horizon and the singularity. The event horizon is the boundary beyond which nothing, not even light, can escape. And the singularity is a point where space-time curvature becomes infinite. Before we try to draw its Penrose diagram, let's see what happens when we fall in. This animation is created by Andrew Hamilton from the University of Colorado Boulder and is linked below if you want to take a closer look. So as we enter the black hole, at first you'll see an Einstein ring, caused by the gravitational force of the black hole distorting the space-time around it. This red grid represents the black hole's horizon. The yellow region on the map now means that we're in the innermost stable orbit. Inside of it, circular orbits become unstable. We're in free-fall orbit, so we'll continue our fall into our black hole. Now, as we fall through the event horizon, you might think that we would fall through the red grid, which represents the horizon. But actually, the red grid still is ahead of us, and the horizon will split in two. Around us, everything would look dimmer and redder because of the tidal effects of the black hole's gravity. The tide would stretch you vertically and squeeze you in the middle, known as spaghettification, because you would look like a spaghetti. Similarly, the photons above and below you would be redshifted with their light stretched out. Just like how the huge tidal forces are stretching you out, falling into a singularity doesn't quite look like falling into an infinite point. Rather, it looks more like you're approaching a flat plane. Okay, so that was a lot to digest. Feel free to rewatch the video in the link below. But now we can actually depict this entire process and the complicated things that we've seen, all on a 2D Penrose diagram. Let's start by drawing the basic structure of our Penrose diagram. We begin with a square, similar to what I showed before, to represent the entire spacetime of the universe just before the black hole. Now, let's add the event horizon. The event horizon is represented by a diagonal line running from the center of the square to the top corner. This line marks the boundary beyond which nothing can escape. Next, we can add the singularity. The singularity is depicted by a squiggly line at the top inside the event horizon, representing where space-time curvature will become infinite. Now, this looks like a line. It's not a point, similar to what we saw in the video. Outside of the event horizon, we have the normal universe, and inside we approach the singularity. So let's see what happens when you, represented by this dot, falls into the black hole. Remember when you fell past the horizon and it wasn't the red grid but somewhere completely else? This is called the anti-horizon. It's an illusion of the real horizon. As you fall into the black hole, the anti-horizon will always remain ahead of you. The true horizon is only visible after you fall into it. As you, a free-falling body, crosses the event horizon, all paths lead inward. This diagram also shows how a singularity is not just a point, represented here. All of the ideas from the video can easily be expressed on this 2D diagram. In our previous example, we looked at a non-rotating black hole, but a more realistic model would be to look at rotating black holes, which is the case for most black holes in the universe. These are called Kerr black holes. Now, this rotation introduces new features that define this type of black hole, including a ring-shaped singularity, an inner and outer event horizon, and an ergosphere. The ergosphere is a mind-boggling region just located outside the event horizon, where space-time itself is being dragged around by the black hole spin. In fact, this phenomenon, known as frame dragging, carries material faster than the speed of light, so that everything, including light, moves along the black hole's rotation. They can never be stationary. Therefore, if an object passes from outside the black hole into the ergosphere, it can still be ejected from the black hole by gaining energy from its rotation. Rotating black holes are bizarre, because if we solve for Einstein's equations of relativity in this scenario, we can theoretically find paths that could lead to other regions of spacetime, linking to other universes or different parts of our own universe. This includes a black hole, a white hole, a parallel universe, or even wormholes. If you want to hear more, you should definitely check out my second special relativity video. In fact, if we zoom into one part of this diagram, this looks similar to the Kruskal coordinates that I described in that video. we can now explore the extended structure of spacetime around this rotating black hole, which gives us a more complete picture of the spacetime geometry. We know that the movement of light is represented by 45-degree angles, so we can travel around like this. But be careful, once we pass the black hole's inner horizon, not even light can escape. Then we're doomed to enter the singularity. But let's say that we could continue our journey into this inner anti-horizon here and actually emerge out from a white hole. We can then continue our journey and enter this block here. This is a universe, but it's definitely not the original universe that we came out from. We've discovered a whole new universe by traveling through a rotating black hole. We can actually keep going on, entering a black hole, emerging from a white hole, entering a new universe, and so forth. Which means that the full Penrose diagram for a rotating black hole can stretch infinitely. You might also notice that there are blocks representing parallel universes here. But these are inaccessible because they would require us to travel at angles more than 45 degrees, meaning we would have to travel faster than the speed of light. But the fact that there are these regions here means that there could potentially be these universes that would remain unattainable to us forever. Now, this idea of parallel universes or white holes is still theoretical. To determine if these solutions are feasible, we would need a quantum theory of gravity. 3 out of the 4 fundamental forces of our universe, electromagnetism, the strong nuclear force, and the weak nuclear force, have quantum descriptions, but there is none for gravity. This will require scientists to measure and analyze gravity on microscopic levels, such as studying gravitons, these particles that would mediate the gravitational force. Until then, Kerr black holes and their Penrose diagrams are just a purely theoretical, yet very exciting feature of our universe. Thanks so much for listening and for all of the video recommendations so far. This one was definitely the most mind-boggling topic to explain. Comment down below if you have any feedback or questions, and don't forget to follow me on YouTube for more nerd content. See ya.